Good morning, students. Let us learn the new title, which is nothing but the Dirac equation. So this is the extension of Unit 8, and this is the continuation. And in fact, we learned in Unit 8 about relativistic quantum mechanics. Especially, we learned relativistic equations, two major equations we learned. So one was about Klein Gordon equation, which is second order differential equation in space and time. Of course, symmetry in space and time. It couldn't explain the spin of particle. Also, it couldn't explain about the negative probability. So this discrepancy was removed by a Dirac equation. So which we learned in the last unit thoroughly. So in Dirac equation, it's a very famous Hamiltonian which he introduced beautifully and boldly, and which includes the spin automatically. So this is a consequence of a spin concept in Dirac equation, Dirac Hamiltonian, alpha and beta. And alpha represents the Pauli's spin mass, and beta is the fourth component of a vector, which is nothing but your identity matrix. So alpha and beta together will have some certain properties. They will apply certain properties. For example, alpha and beta, they anti-commute with each other. They themselves will commute with each other, but with others they will anti-commute with each other, and they will have Hermitian property. The traces will be zero, and all those things. So this is what we learned. And as I said just now, this is the continuation of relativistic equation, and we are going to introduce gamma matrices. So we are going to introduce the gamma matrices soon. These gamma matrices include alpha and beta. So what are the properties they apply for alpha and beta? The same property also will be good for gamma. Okay, the same thing. Gamma matrices are traceless matrices, Hermitian matrix. Then we can say that they anti-commute with each other. They are all Hermitian. So what are the properties for alpha and beta? The same properties also will hold good for gamma matrices, because gamma matrices include alpha and beta, which we are going to see now. So in this class, we are going to discuss covariant form of Dirac equation. Covariance of Dirac equation. In some other book you may read like this. So covariant form of Dirac equation. This is just a representation. Probably you would have learnt in tensor about the covariant vectors, covariant tensors, and contravariant tensors, and mixed tensors. So probably you would have learnt. Covariant means subscripts. The indices will be bottom at the subscript. Contravariant means superscript. For example, we have a scalar. Scalar represents a magnitude, no direction. So we have a single number. Okay. Then when you go for a vector in terms of matrices, either you can represent it in terms of a column vector or a row vector. Okay. So this is of a rank of 1. Scalar of rank of 0 tensor. Vector is of rank 1 tensor. Rank 2 tensor will be matrices, 2 by 2 matrices. 2 by 2 matrices are represented in terms of rank 2 tensors. Rank 3 tensor will be 3 by 3. And those tensors can be represented in terms of, this is just a representation, in terms of either covariant vectors or contravariant vectors. Covariant means invariant in Lorentz transformation. So any quantities which are invariant are called tensors. Okay, any quantities which are invariant are called tensors. Or otherwise we can say that we are going to transform from one coordinate into another coordinates. The physical laws will be same. The physical laws will be constant. So this is called invariant of Lorentz transformation. Or otherwise we can say this is covariance. Okay, simply meaning. So we are going to have the titles in this unit Dirac equation are covariant form of Dirac equation, properties of gamma matrices, traces, adding the diagonal elements, relativistic invariance of Dirac equation, probability density, current 4 vectors, bilinear covariant, Feynman's theory of positron, elementary ideas only without the propagation formulation. Okay, so these are the titles that we are going to cover in this unit, and this is small unit, but which will have a lot of meaning. As I said, this is a continuation of last unit. Okay, so covariant form of Dirac equation. So as I said, the physical laws should be same in all inertial frames. So in accordance with the principle of relativity, physics must look the same in all Lorentz frames. We are going to transform from one coordinate into another coordinates. Both the physical laws, the results must be the same. This means that the physical theories that are consistent with the principle of relativity must have the same form in all Lorentz frames, that is, they must be covariant. So covariant means invariant in Lorentz transformation. We are going to examine the covariance of the Dirac equation in this class. So in this derivation, we mainly deal with the Dirac wave function psi, which is understood to be a 4-component spinor. So we are going to have a 4-component spinor. Okay, psi. Look at this component C x mu. As I said just now, mu x mu, this is your covariant. This is written as, it's a representation, it's written as subscript. Okay, suppose mu is in the upper top superscript, then that's called contravariant vector. So this is covariant. Okay, and of course symmetry in space and time. We know that the Hamiltonian, which Dirac used in first order differential equation, which is symmetry in space and time. So x mu equals r comma ict. R stands for x, y, z. So we have x, y, z and t. So 4 coordinates exist. So we learnt in third unit as Minkowski space. Okay. x1 stands for x, x2 stands for y, x3 stands for z, and x4 will be your time coordinate ict. Okay. So mu is the continuation 1, 2, 3, 4. 1, 2, 3, 4. 3 for space coordinates and 1 for time coordinates. So totally we have 4 coordinates. Space and time are in symmetry. The covariant form of Dirac equation. We know that the simplest Dirac Hamiltonian is a linear and homogeneous equation. In the momentum and mass is given by this equation. So you have C times alpha dot p plus beta m naught c squared. So this is your Dirac's Hamiltonian, which is a linear equation. As I said just now, invariant under Lorentz transformation is nothing but the term covariance. So covariant form. Okay. Now we know that the eigenvalue equation h psi equal to E psi on this Hamiltonian is given by E operating on psi, that will give you C times alpha dot p plus beta m naught c squared acting on psi, which depends on both r and t. Okay, both r and t. And there's a mistake here, there will be no zero. Okay, so there is a mistake here, so there will be no zero. So E psi equals h psi, that's all. Okay, so there is no zero here. Using the energy operator, so we can convert this E as I h cross partial d psi by dt. We are going to convert this one into energy operator. We can write this equation exactly like this. This right hand side operates on psi. So d by dt on the left hand side is not a Lorentz scalar, because the time t represents just one component of the 4 vector. So your x mu equals r comma ict. So it is not a Lorentz covariant. So this alone is not a Lorentz covariant. Okay. So we have to go only with x coordinate as well time coordinate. To put into a covariant form, so now we are going to convert this p equals minus I s cross del. Okay, we know the operator, expression for operator. I am going to substitute as p equals minus I h cross partial d by dx. So I can write p exactly in terms of px, py, pz. Okay, here also I can write this as alpha x, alpha y, alpha z. So there will be 3 coordinates. So I can write this as alpha k d psi by dxk. Other terms are let it be like this. Where p equals minus I h cross del. Okay, so you have minus I h cross c times alpha k d psi by dxk. Is it okay? Where k equals 1, 2, 3. 1 stands for x. 2 stands for y, 3 stands for z. So 3 coordinates in space, and plus beta m naught c square psi. Okay, now we are going to multiply this equation by beta by c from the left. So we are going to multiply this equation by beta by c. So I h cross beta by c d psi by dt, which is equal to minus I h cross beta by c. That c and this c will cancel. You have beta alone. So alpha k d psi by dxk. What is alpha? Alpha is connected with Dirac spinors. Don't forget. So sigma x, sigma y, sigma z. So it's connected with Dirac spinor. So alpha k d psi by dxk plus you have beta by c. One c and another c in the denominator will get cancelled. So you have beta squared m naught c squared. Now just divide by h bar. Divide this equation by h bar. Will give you I. H bar will get cancelled. You have beta by c d psi by dt, which is equal to minus I. H bar will get cancelled. You have beta alpha k d psi by dxk plus your beta squared. Beta squared equals 1. We have learned from the third unit. Okay, alpha squared, which is nothing but your alpha x squared, which is equal to alpha y squared, which is equal to alpha z squared, which is equal to 1. Beta squared also equal to 1. So beta squared is nothing but, as I said, this identity matrix. So beta squared will be 1 0 0 minus 1. You multiply with 1 0 0 minus 1, you will have 1 0 0 1, which is nothing but 1. So beta squared is nothing but 1. So beta squared can be replaced with 1. Now the remaining term will be m naught c. You are going to divide this by h cross. So you have h cross acting on psi. Any doubt? Equation 9.6. Very simple. Now multiplying and dividing by I. So multiply and dividing by I, because we need to get ICT. So no other way. ICT stands for fourth coordinate. Okay, time coordinate. So that's why we are going to divide this by I. So this will become I square. Okay, I square divided by I is there. So you have IC. Okay, so we can write this equation as minus beta d psi divided by d of ICT. I have brought everything inside. Now this represents the fourth coordinate. Simple one. Any doubt? Time coordinate becomes now ICT, fourth coordinate. Now what of this term? We have written exactly the same as that of 9.6. Okay, right hand side we have not disturbed anything. Now we are going to take this term as gamma matrices. We know that alphas are matrices, beta also is a matrix, and multiplying these two, that is vector multiplication. Okay, that will give you gamma. So gamma, as I said earlier, gamma contains both alpha and beta. So we are going to represent this gamma matrix as minus I beta alpha k. Very, very, very important. Okay, what are the properties of alpha and beta? The same properties will hold good for gamma too. Very simple logic. Okay, we have already learned many properties, and those properties will apply for gamma too. So we have minus I beta alpha k is represented as gamma d psi by dxk plus m naught c by h cross psi. So introducing, now we have introduced gamma matrices. So defined by, so we have 4 matrices, as I said. Alpha will have 3 and beta will have 1. So we have 4. The fourth matrix is nothing but your beta, which is nothing but 1 0 0 minus 1. Then earlier I said that your alpha is connected with 3 spinors: sigma x, sigma y, sigma z. So we can say that sigma 1, sigma 2, sigma 3. So this is in the representation of alpha k in terms of sigma. Okay, this one. So we'll see now. So your gamma k stands for 1 2 3 space coordinates. Okay, minus I beta alpha k, which is equal to minus I. Beta is written in terms of matrix 1 0 0 minus 1. Your alpha k is nothing but 0 alpha k 0. So you multiply, matrix multiplication will give you this. Is it okay? Minus I, this will become plus I. You just matrix multiplication will give you 0, and this term will be I alpha k, and this term will be minus I alpha k and 0. Don't forget, very important thing is k will go from 1 2 3 space coordinate, and mu goes from 1 2 3 as per the fourth one, time coordinate. So mu stands for 1 2 3 4. First 3 stands for space coordinate, the last one stands for beta. Okay, Is it okay? Any doubt? So k equals 1, 2, 3 and mu equals 1, 2, 3, 4. Wherever you find mu, you have to remember that this is 1, 2, 3, 4. Wherever you find k, you have to remember this is 1, 2, 3. Okay. So we know that x mu is nothing but your x, y, z, comma, ict. 4-dimensional coordinates. So we know that 4-dimensional coordinates exist. So 2 by 2, if at all 2 by 2, then we will go for only even numbers. Can you remember in the last section we dealt? So this will become 4 by 4. So those will come only even numbers. Okay. So now this term. So instead of this we can write as gamma. So we can write this as beta. Beta as gamma 4. Correct? Beta as gamma 4. So you have gamma 4 minus gamma 4 d psi by dx4, which is equal to gamma k d psi by dxk plus m naught c by h cross I. Now multiplying with the minus sign and bringing the right hand side to left hand side. We can do either way. You can take this term to that side or bring those terms to this side and multiply with the minus sign. That's all. You will get this equation. So you will have gamma 4 d psi by dx4, okay, time coordinate, gamma k d psi by dxk space coordinate plus m naught c by h cross I. Is it okay? So look at this is x4. x4 stands for ICT. It's a time coordinate. Okay. So look at this equation. We have first order differential equation, both space and time. So symmetry exists both in both space and time. Very clear that it's a linear equation and also it's a homogeneous equation. So now this equation can be written as exactly together. As I said, can you remember 1, 2, 3, 4 together we can write as mu. So we have written as mu. This is covariant vector. Okay, gamma mu. I repeat, together, this is 1, 2, 3, this is fourth one. Add together, this can be written as 1, 2, 3, 4. So gamma 4. This is the covariant vector, covariant tensor. Okay, so gamma mu d psi by dx mu plus m naught c by h bar psi equals 0. This is the covariant form of Dirac's equation. Covariance of Dirac's relativistic equation. Any doubt? So as I said, x mu stands for 3 space coordinates x, y, z and time coordinates nothing but your ICT. So we can write this with the expansion as exactly like this. You have a time coordinate, x coordinate, y coordinate, z coordinate. So this is what we have written earlier. This can be replaced with a summation. Summation goes from mu goes from 1 to 4, 1, 2, 3, 4. But Einstein convection of indices that says that we can write this as exactly like this, where mu is a series 1, 2, 3, 4. So we can write instead of summation, this is Einstein convention of making the index. So we can write, removing the summation, we can write exactly like this. So this equation contains Lorentz invariant term and parity transformation time reversal charge contribution can easily be found from this equation. So this is Lorentz invariant covariant form. Okay, any doubt? Equation 9.12. So now very important thing is properties of gamma matrices, the next topic. So we are going to learn today, as I said, covariant form of Dirac's equation. That's the first one. And second one will be properties of gamma matrices and traces of gamma matrices. So 3 topics that we are going to learn. Okay, properties of gamma matrices. What are the properties of alpha and beta? The same properties will hold good for gamma 2. So that's the idea. Okay, now we know that gamma k equals minus I beta alpha k. Okay, we know already this. So minus I, your beta is here. Okay, beta is identity matrix, we know already. I0, 0 minus I. And alpha k, as I said, this is connected with the spin as. So 0, sigma k, 0. Your gamma 4 will be identity matrix, which is nothing but your beta. And sigma k goes from 1, 2, 3, which are nothing but your Pauli spin as. Okay, so we know that sigma k, sigma 1, so far that will be for gamma 1. We are going to introduce now. See, gamma 1 is nothing but sigma 1. So 0 minus I sigma 1, gamma 1. Just multiply these two with minus I, you will get 0 minus I sigma 1, I sigma 1, 0, 2 by 2 matrix. When you are going for gamma 2. This becomes minus I sigma 2. Here you have I sigma 2. 0, 0, diagonal wise. And gamma 3, the same thing. 0, minus I sigma 3, I sigma 3, 0. What are the traces of the matrix? Any guess? Traces of the matrix. Trace of this matrix will be 0. Trace of this matrix will be 0. That one also 0. What about gamma 4? That also 0. So gamma matrices are traceless matrices. Simple idea. So important one more question. Okay, traceless matrices. All gamma matrices. Gamma matrices contain with gamma 1, gamma 2, gamma 3, gamma 4. All the matrices, if you are going to add the diagonals, answer will be 0. So gamma matrices are traceless matrices. So there is no trace at all. We will see later. Okay. These matrices satisfy the following anti-commuting rules. Gamma matrices themselves will commute, whereas with other gamma matrices it will have anti-commute. I repeat, when you are going to have gamma 1, gamma 1, okay, gamma 1, gamma 1, this will commute. Gamma 1 with gamma 2, gamma 1 with gamma 3, gamma 2 with gamma 3, or gamma 3 with gamma 4, they will have anti-commute. So the matrices satisfy the following anti-commuting rules. Anti-commuting, the symbol will be curly one. For commuting, symbol will be square bracket. See, this is curl bracket. See, I have written as a curl bracket. See here, it's a curly one. For square bracket, we will go only with a commutation. So this is for anti-commuting. So gamma mu, comma gamma nu. Okay, gamma nu. So which can be written as AB plus BA. For commuting, AB minus BA. For anti-commuting, this will be AB plus BA. Okay, suppose if mu is not equal to mu is not equal to nu, according to Dirac delta function, this will become 0. Okay, so mu is not equal to nu. That means AB plus BA equals 0. So your answer is 0. Suppose if you have mu equals nu, then this becomes gamma mu squared plus gamma nu squared, whatever may be. What is gamma nu squared plus gamma? Gamma nu squared is 1. Gamma nu squared also will be 1. Gamma mu squared also will be 1. Gamma nu squared also will be 1. 1 plus 1, 2. So when it is equal, answer is 2. Very important one more question. Is it okay? So they will follow only anti-commuting rules. Okay. Now, for example, gamma 1, gamma 2 plus gamma 2, gamma 1. We will check whether gamma 1 plus gamma 2 plus gamma 2, gamma 1 is equal to 0 or not. We are going to check. So this is for gamma 1. This is expression for gamma 1. This is connected with sigma 1. This is for gamma 2, which is connected with sigma 2. So your gamma 1, gamma 2 plus gamma 2, gamma 1. Is it okay? So AB plus BA, anti-commuting. So your gamma 1, gamma 2 plus gamma 2, gamma 1. So if I are going to multiply matrix multiplication, that will give you answer as sigma 1, sigma 2, 0, 0, sigma 1, sigma 2. Correct? See, you have 0. First term will be, come on, 0 minus I sigma 1 multiplied by I sigma 2. I into I squared minus 1. So already one minus is there. So plus. So sigma 1, sigma 2. The next term will be 0. The next term will be sigma 1, sigma 2. Similarly, you can go for the next one. Okay, BA. You can go for sigma 2, sigma 1, 0, 0, sigma 2, sigma 1. You are going to add these two according to this. You are going to add these two. You will get the answer as exactly like this. What is sigma 1, sigma 2 plus sigma 2, sigma 1? Just now we were looking at 2. It is 0. So 0, 0, 0, 0. The answer is 0. If it is not equal, mu is not equal to nu. Is it okay? Similarly, you can go for 1, 2, 3. For other indices also we can go. We have done for gamma 1, gamma 2. You can do it for gamma 1, gamma 3. You can do it for gamma 1, gamma 4. You can do it. Gamma 2, gamma 3, gamma 3, gamma 1. You can do it. Doesn't matter. So everything will go only according to this rule. So they will anti-commute with each other. Suppose if mu equal to nu, okay, that is 1 equals 2. So in this notation we have 1 equals 2. If 1 equals 2, this becomes 2 sigma 1 squared. This becomes 2 sigma 1 squared. You pull 2 out. 2 sigma 1 squared out. So that will give you 1001, which is nothing but 2 del mu nu. Any doubt? So sigma 1 squared equals 1. Any doubt?